Here, and in today's lesson we will talk about the microservice architecture, API gateway considerations. This will be a very important topic to understand what is microservices, how to design API gateway, and what we should keep in mind during we are designing the API gateway for any kind of microservices architecture. Service, the API gateway and other elements are integral part of microservice architecture. In today's extremely competitive business environment, customers are more demanding than ever and will abandon a business that is too slow to respond. This has put an onus on IT to deliver solutions that provide a holistic and uniform experience to the customer across all business channels. Microservice architecture has the potential to address this business challenge. It is all about achieving speed and safety at scale, and it provides the flexibility to pick and choose technology for implementing a solution. This approach positions IT as a business partner rather than in a traditional support role. Microservice architecture consists of a suite of independently deployable, small, modular, and composable service. Each service runs a unique process and communicates through a well-defined, lightweight mechanism to serve a business goal. It aligns with the business to deal with changes in agile fashion, matches business changes with agile responses, and delivers solutions in a decentralized manner. In addition to modular services, the API gateway and other elements are very important. Like in the picture, we can see that we have microservice A cluster, B cluster, and C cluster, but there are other elements also, like monitoring and analytics, security access management, API gateway, service router, service registry, etc. In this video, we will discuss about these topics. Basically, the API gateway is a reverse proxy to microservices and act as a single entry point into the system. It is similar to a facade pattern from object-oriented design and similar to the notion of an anti-corruption layer in domain-driven design. It makes the process of API design, implementation, and management considerably simpler and more consistent. The gateway helps to address some of the key concerns, including number one, how to deal with features such as security, throttling, caching, and monitoring at one place. Two number point, how to avoid chatty communication between client and microservices. Point number three, how to satisfy the needs of heterogeneous clients. 4. How to route request to backend microservices. Next, how to discover working microservices instances. How to discover when a microservice instance is not running. With a single entry point into the system, it becomes easy and manageable to enforce runtime governance such as common security requirement, common design decision, and real-time policies such as monitoring, auditing, and measuring API usage and throttling. The gateway abstract microservices from their consumers, which provide flexibility to freely add or remove microservices in instances to adapt to the local demand of microservices. There may be an instance when different consumers of the service require particular data or have it in a special format. For an example, e-commerce mobile app shows product information and availability of product on the product details screen. But the desktop website version of the same e-commerce site shows recommendations in addition to the product information and availability. There are mobile apps where one understands XML payload and other understand JSON. The API gateway is the best place to address these transformation requirements, which can be accomplished by providing application-specific APIs for the same business feature at the gateway level. A one-size-fits-all approach would make it hard to extend functionality as the degree of diversity increases. The gateway also helps by recording data for analysis and auditing purpose, load balancing, caching, and static response handling. The diagram shows how the gateway typically fits into the overall microservice architecture. We can see that many type of clients like desktop, mobile, or any other API hitting our microservices. First, like facade of microservices, single entry point, coarse consumer driven APIs, protocol data transformation, service registry and discovery, security and authorization, request dispatching and load balancing, orchestration, throttling, monitoring. This picture demonstrates how a gateway typically fits into the overall microservice architecture. It gateway will handle all these kind of requirements, and finally it move to the original microservice, original our resource service, which get the data, compute it, run the business logic, and make final output for you. Requirement of any enterprise solution. At a certain point in the architecture, the best options available for authentication, authorization, threat protection, message protection, etc. must be chosen. Federated identity is the preferred solution for implementing authentication and authorization in microservices architecture. Each microservice does not necessarily need to obtain and store users' credentials in order to authenticate them. Instead, microservices can be used in identity management system that is already storing a user's identity to authenticate the user. This approach allows the decoupling of the authentication and authorization functions. It also makes it easier to centralize these two functions to avoid a situation where every service must manage a set of credentials for every user. There are three major protocols for federated identity. One is OpenID, another is SAML, and third one is OAuth. The figure shows the security architecture using OAuth 2.0. Every API request is authenticated at the gateway layer on behalf of the end user. The application client first grabs an access token from the authentication server by presenting credentials. This access token is then passed along with the API request in authorization HTTP header. The API gateway then validates the access token with the authorization server. The JWT token, which contains the claim for the user, is then passed to backend microservices. Backend microservices then use the information inside the JWT token for authorization purpose. The same JWT token is passed along when one microservice communicates with another microservice. The has the potential to be confused deputy problem. As every microservice is relying on the API gateway for authentication, ideally every microservice should be authenticate the token as received from its caller, gateways, or the microservice. There is a trade-off between security and performance. The architecture leans toward performance as there are other mechanisms to mitigate the towards service registry and service discovery. Ease in scaling is one of the key advantages of microservice architecture. You will keep adding or removing microservice instances to adopt to incoming traffic. In addition, your team may be adding new microservices or refactoring existing microservices into multiple. Service instances have dynamically assigned network locations. So service registry become an important factor of any microservice architect. The service registry helps to keep track of these instances. It is a database containing the network locations of the service instance. Every service instance registers itself on startup and deregister on shutdown. The API gateway uses this information during service discovery. In the figure below shows service registration and discovery. There are two models for checking the status of service, pull model and push model. Although some of the registries support the pull model, it is not recommended as it puts an additional load on the registry. Moreover, it is the service responsibility to update the registry about its unavailability to serve the request. As a critical component, the service registry needs to be highly available. You should plan for a cluster of registries that uses replication to maintain consistency. Never try to cache the network locations obtained from the registry at the registry user. That information eventually become out of date, causing clients to become unable to discover service instances. Service discovery. The number and the location of service instances is dynamic. Consequently, your client code needs to use a more elaborate service discovery mechanism. There are two main service discovery patterns. One is the client-side discovery and other is server-side discovery. Server-side discovery is preferred for various reasons. One, it removes the discovery burden from the client so that it can focus on business function. If you have multiple clients, then you need to code and maintain the discovery code for each client. It reduces number of calls over the internet. So there are two main service discovery patterns. One is the client side and another is the server side. We can see in the diagram here. In the client side, API gateway, one is the client side discovery, in which client registry aware client talking to the service registry, getting the real endpoints, then talking to API gateway. In turn, API gateway forward the request to the microservice resource servers. The other picture shows below server side discovery. In the server side discovery, client is talking to the API gateway. API gateway in turn resolving or discovery the service from the service registry. After the discovery, it passes request to the orchestrate across multiple fine-grained microservices to accomplish a business use case. As shows in the figure below. One second. As shows in the figure, there are two options for implementing the orchestration using the API gateway as the orchestration layer or coding orchestration in a separate microservice. You should avoid orchestration at the gateway layer. It violates the single responsibility principle, and in case of scaling the API, you will have to scale the gateway along with orchestrator microservice. Some of the API gateway have little to no capability for orchestration. Although it is discouraged to use orchestration at the gateway layer, if you still want to use it for whatever reason, then there should not be any business logic involved while orchestration. Often microservices have to deal with different clients on the front end. They have different needs from both at protocol level like SOAP, REST, JSON and XML and the data perspective. Similarly, when you are moving from monolithic to microservices, backend services may understand different protocol. Similar SOAP, REST, AMQP, etc. The API gateway provides a place for data transformation where messages can be translated between backend, API, and app formats and protocols. The gateway provides a central data transformation point through which all traffic is translated for requested payload transformations, header transformation, protocol transformation. Develop your transformation adapters as reusable component. Also, do not try to code all different clients' needs in a single API. You should think of creating client-specific APIs with pluggable transformation. And data analysis helps in understanding, estimating the load of the system. In turn, this helps in scaling the gateway and underlying services accordingly. The gateway can scale both horizontally and vertically. An API gateway, being load balanced, runs the same configuration to virtualize the same API and executes the same policies. If multiple API gateway groups are deployed, load balancing should be across groups. The API does not impose any special requirements on load balancers. Loads are balanced on a number of characteristics including the response time or system load. The execution of API gateway policies is stateless, and the route through which a message taken on a particular system has no bearing on its processing. Some items like caches and counters, which are held on a distributed cache, are updated on a per message basis. This helps the API gateway to operate successfully in both sticky and not sticky mode. The distributed state poses a certain restrictions in terms of active, and active passive clustering. For example, in case the counter and cache state is important, the system should be designed to make sure at least one API gateway is active at all the times. This means that for a resilient high availability system, you should employ a minimum of at least two active API gateways at any given time. Extra is passive mode. The API gateway also ensures zero downtime by implementing configuration deployment in a rolling fashion. This means while each API gateway instance in the cluster or group take a few seconds to update its configuration, it stops serving new requests. But all existing in-flight requests are honored. Meanwhile, the rest of the cluster or group can still receive new requests. The load balancer ensures that requests are pushed to the nodes that are still receiving requests.